Thank you for listening to my presentation. My topic is evaluating and improving context and attention distribution and multi-turn response generation using self-contained instructions. And this is the problem that we want to solve. In human dialogues, it is very common to contain unimportant utterances, such as the two utterances in red. In this dialogue, the main topic is about solving a technical problem that Gulla faces in the Linux system. While the first two utterances are irrelevant, our task is to generate a response based on the previous utterances in this dialogue. In this case, to generate a response for Gulla, we want the model to ignore the irrelevant utterances, which are the first two utterances in red. We call it the ability of context attention distribution. There are lots of work dealing with generating responses. However, most of them regard multi-turn dialogues as single turns. Usually, people concatenate the dialogue histories line by line to transform from multi-turn to single turn. There are some works that deal with multi-turn conversations with hierarchical models. In this work, we will propose an evaluation metric for a model's ability on dealing with multi-turn dialogue based on the context attention distribution. This ratio is called DAS ratio. It works by measuring the ability to distribute more attention to important utterances. We then propose an optimization strategy that minimizes the attention paid to unimportant utterances. We add self-contained distractions during the training process and optimize this. The strategy can be easily added to existing models. Our base model is LSTM, since most multi-turn conversational agents are built upon LSTM. We have reproduced three methods on dealing with multi-turn conversations. Non-hierarchical, which means that we do not deal with multi-turn and just concatenate utterances in each turn. Static attention loss, where that context.
Excuse me, Dr. Yujie. The slides are not moving.
Not moving? Is it moving now?
Yep, now it's moving. Yep, thank you.
Okay, thank you. Static attention loss, where the context vector is calculated between the last utterance in the dialogue and all the other previous utterances in the dialogue. And we have dynamic attention loss, where the context vector is calculated between each token in the response and all utterances in the dialogue history. There is also an added method, which is called utterance integration. If utterance integration is applied, there is an LSTM layer that integrates all utterances in the dialogue, and this vector will be input to the decoder. Otherwise, the vector of the last token in the dialogue will be input into the decoder. Now I will introduce our evaluation metric. To calculate the DAS ratio, we need to first form a distracting test set. We add distracting utterances to the original training corpus. We have three sources of getting distracting utterances. The first is that we pick them randomly from the training corpus. The second is that we pick the frequent words from the training corpus and form an utterance using these words. The third is that we pick the rare words from the training corpus and form an utterance using these words. After forming the distracting test set, we will calculate the attention score. The attention score are calculated on each utterances, which indicates how much attention is paid to each utterances. Afterwards, we calculate the DAS ratio from the attention score. Here is an example of how a distracting test set looks like. In a random test set, we get the distracting utterances from the training corpus randomly. The probability of inserting the distracting utterances are 0.5, 0.7, and 1.0. In each dialogue, we only insert 2 or less distracting utterances. In a frequent test set, we use the utterance, "Why should I help you?" "Have my right" as the distracting utterances, since they are frequent words in the corpus. In a rare test set, we use the utterance, "Would you have lunch?" and "I should have lunch" as the distracting utterances, since lunch is a rare word in the training corpus. Query is the last utterance in a dialogue. Next, we calculate the attention score. With different attention methods, we have different ways of calculating attention score. Generally, it is all about calculating how much attention is distributed to each utterance. And finally, we use DAS ratio to calculate the performance of each model on dealing with multi-turn conversations. It is the ratio of the attention scores of the distracting utterances and the other utterances in the dialogue history. The lower the DAS ratio, the better the model performs. Next, we introduce our optimization with self-contained distractions. Self-contained distractions are distracting utterances that are randomly picked from the training corpus. The utterances are inserted to the training corpus with 3 probability levels, 0.5, 0.7, and 1.0. Inserting locations are randomly decided. We calculate an attention loss on these distractions and minimize the loss during the training. This is a formula to calculate the attention loss. We calculate attention loss with different formulae for different methods. Next, I introduce our experiment settings. For the dataset, we used the Ubuntu chatlog dataset. We tested 5 model variants with our optimization strategy. We use 3 inserting probabilities for our optimization strategy. The results show that for the random distracting test set, the DAS ratio is the lowest for the model with static attention loss and utterance integration, and an optimization inserting probability of 0.7. For other distracting tests, the results are rather random. We also show the results for the static utterance integration model with or without attention loss. The DAS ratios are the largest when training without the attention loss and without the distractions. The DAS ratios are lower when training with distractions, while without attention loss. And the DAS ratio is the lowest when training with the attention loss.